We are going to start module 3 of chapter 8. In this module, we shall discuss the isoperimetric problems. So far, we have discussed different problems in which we find the extremals where we choose the arguments functions arbitrarily except for the end conditions. But if there are some constants, then we cannot choose the arguments functions arbitrarily except for the boundary. In such cases, the problems are known as isoperimetric problems. Now we shall discuss the detail about it. In this module, we shall discuss what is the isoperimetric problem. Now we discuss the method of solving such problem. Next, solution of some isoperimetric problems will be obtained. Conditions for extremizing a definite integral for the variable endpoints will also be discussed. Now, isoperimetric problem, let us define it. If there are constraints in the problems of extrema, then we have to find the maximum or minimum of a function of several variables g function of x1, x2 up to xn, where the variables x1, x2 up to xn are connected by some relations or conditions termed as constraints or restrictions. The problems that we have considered so far find the extremum of a functional where the argument function can be chosen arbitrarily except for the boundary or end conditions. But if some constraints are imposed on the argument functions of the variational problems, obviously except for the end conditions, the problems are then termed as isoperimetric problems. Iso means same, perimetric comes from the word parameter. In isoperimetric problem, it is required to find a closed curve of given length which encloses a minimum area. I have already mentioned that given length, this is the constant, that is we cannot choose arbitrary length, it is already prescribed. Consider the simplest isoperimetric problem which consists of finding of a function f function of x that extremizes the functional I1 depends on y which depends on x is equal to integration x1 to x2 f function of x y y dash into dx, y dash means ddx of y subject to the constraint that is another integral given by capital I2 which depends also on y, y is dependent on x equal to function of x1 to x2 g function of x, y and y dash to dx assumes a prescribed value and also satisfy the prescribed end conditions, that is y at x1 equal to y1 and y at x2 equal to y2. To solve this problem, we use the method of Lagrange multipliers. For this, let us form a function h small h function of x, y and y dash which is given by small f function of x, y and y dash plus lambda into g function of x, y, y dash, where lambda is an arbitrary constant. This is known as Lagrange multiplier. Now, the problem is to find the extremal of the functional I star depending on y which depends on x equal to integration x1 to x2 h function of x, y, y dash into dx subject to the constants except the end conditions. Now, Euler-Lagrange equation gives first order partial derivative of h with respect to y minus ddx of first order partial derivative of h with respect to y dash equal to 0. This is a second order equation. So, the solution of this equation contains two integrating constants. Moreover, there is another unknown quantity which is lambda known as Lagrange's multiplier. So, these three unknowns are to be determined using the end conditions given by 8.10 and the constraint relation given by 8.9. Let the parametric equation of the curve be x equal to x function of t, y equal to y function of t, t is the parameter. Then the area enclosed by the curve is given by I1 equal to half integration t1 to t2 x into y dot minus x dot into y dt. We get this from the formula of area. X dot means ddt of x, this is the ordinary derivative of x with respect to time t. Similarly, y dot is ddt of y. As the curve is closed, we have x at t1 equal to x0 equal to x at t2 and y at t1 equal to y at t2 equal to y0. The total length of the curve is given by I2 equal to integration t1 to t2 square root of x dot square plus y dot square into dt. We have to optimize I2 also. Let us form a new function, that is h. H is given by the combination of I1 and I2, that is h equal to half into x y dot minus y x dot plus lambda into x dot square plus y dot square. This comes from this one, from I1, and from I2 this comes. Lambda is the Lagrange multiplier. This is an unknown quantity. We have to find a curve with given perimeter for which the area given by 1 is maximum. Thus, Euler-Lagrange equations are given by first order partial derivative of h with respect to x minus ddt of first order partial derivative of h with respect to x dot equal to 0. Similar result holds for y. This equation gives differentiating h given by 3 with respect to x, x dot, y and y dot, and putting those values in these two equations, we get these two. If we integrate these equations with respect to time t, we get this equation from this one and this equation from this one. C1 and C2 are arbitrary constants. From this equation, we can get y minus C1 and x minus C2, and after getting this one and this one, if we square it and then add these two, we get it as this one, that is x minus C2 whole square plus y minus C1 whole square equal to lambda square, which is the equation of a circle. Next problem, determine the shape of an absolutely flexible, inextensible, homogeneous and heavy rope of given length capital L suspended at the points capital A and capital B. The rope in equilibrium take such a shape that its center of gravity occupies the lowest position. Thus, to find minimum of y coordinate of the center of gravity of the string, we get I1 which depends on y, y depends on x. This we get this result from the definition of center of gravity. Subject to the constraint I2 which depends on y, y again depends on x, equal to integration x1 to x2 square root of 1 plus y dash square dx equal to capital L, this is constant. Since this is an inextensible string, we have to minimize the numerator of the right hand side of 1, that is we have to minimize this one subject to the condition given by this, given by 2. Now, let us form a new function small h using I1 and I2. This comes from I1, this part comes from I2, lambda is the Lagrange multiplier. This can be written in this way, lambda is unknown quantity. Please note that h is independent of x, there is no x here. So, Euler-Lagrange equation gives small h minus y dash first order partial derivative of h with respect to y dash equal to constant. If we write the constant as k1, we get this equation. After calculating this first order partial derivative and substituting its value in this equation, we get the result given in the next line, that is in this line. Combining these terms and multiplying by square root of 1 plus y dash square both sides, we get this one. This on simplification becomes this. Let us put y dash equal to sin hyperbolic t, t is a parameter, in 4, that is here. Putting this, we get this result. On simplification, this gives this one. As y dash equal to sin hyperbolic t, y dash means ddx of y, this can be written in this way. If we put the value of the differential dy here and the value of y dash here, then after simplification we get this one. On integration, this gives x equal to k1 into t plus k2, k2 integrating constant. After eliminating t from 5 and 6, we have this result. This is our desired curve, which is nothing but a catenary. Please note that there are 3 unknowns, lambda, k1 and k2. These are to be determined using the constraint relation given by 2 and also using the 2 end conditions, which are as the curve passes through the points A and B. So, we have to use the end conditions. In isoperimetric problem, it is required to obtain a closed curve of given length which encloses a surface of minimum area. So far, we have discussed detail about it. In such problems, the endpoints were fixed, they were prescribed, but there are some problems in which endpoints can vary. Let us consider such cases. So far, we have considered the endpoints which were fixed, but now we are interested to consider the case of variable endpoints. It varies only in the y direction. Let the endpoints be variable in the y direction. For this, let us consider the integral capital J depends on capital Y. Please note it. So far we have considered only small y. Here we have considered capital Y. J is given by integral a to b capital F function of small x, capital Y and capital Y dash into dx. Small y function of x is not prescribed at the endpoints. Suppose capital J is stationary for capital Y equal to small y. Let us take this relation between capital Y and small y, where epsilon is a small parameter and eta is a function of x having first order derivative. Then we can write down this integral in this way. Here we have substituted the value of capital Y in terms of small y, capital Y and capital Y dash in terms of small y and small y dash. Then we get this result. Expanding this one, we get these terms. These terms stands for containing terms of order epsilon square and higher powers. If we take the variation of j, we get delta j equal to integration a to b epsilon eta del del small y of capital F plus epsilon eta dash del del small y dash of capital F into dx. Next, we have to integrate this term using the integration by parts. From this, we get two terms, this one and this one. First term has been kept as it is. This term has been written here and these two terms have been written here. We have just arranged in this way. If at capital Y equal to small y, j function of capital Y has a minimum, we must have variation of j equal to 0. This is the condition for extremum. There are 4 possible cases in which this can happen. How? Let us find. Consider figure 8.4. There are 4 figures. In first figure, two curves meet at both points, lower curve small y, upper curve capital Y. Second curve, both figures do not meet at the end points. In third figure, both curves meet at the lower point, but in the upper end they do not meet. In fourth figure, both curves meet at the upper end, but they do not meet at the lower end. End points are considered in those 4 figures at A and B, that is kept constant for 4 figures. Consider first figure. In this case, eta equal to 0 at x equal to A and at x equal to B, since both curves meet at these 2 points. This gives variation of j delta j equal to integration a to b epsilon eta del del small y of capital F minus d dx of first order partial derivative of capital F taken with respect to y dash to dx equal to 0. Please remember that the last term vanishes since eta equal to 0 at x equal to A and x equal to B. As the variation dx is arbitrary, so we get this one equal to 0. for A less than x less than b, which is nothing but the Euler Lagrange equation. For next figure, that is figure 2. In this case, eta not equal to 0 for x equal to a and eta not equal to 0 for x equal to b. Please recall that in this figure both curves do not meet at the end points. By Euler Lagrange equation, the integral on the right hand side of 8.13 vanishes. This finally gives variation of j, that is delta j, equal to epsilon into eta first order partial derivative of capital F with respect to y dash taken at a and b equal to 0. Consider third figure. Here both curves meet at lower end but not at the upper end. So, eta equal to 0 at x equal to a, but eta not equal to 0 at x equal to b. Using Euler Lagrange equation, the integral on the right hand side of 8.13 vanishes in the same fashion. So, we finally have delta j equal to epsilon eta del y dash of capital F equal to 0 at x equal to b. Please note, for eta equal to 0, it vanishes automatically at x equal to a. So, we have only one condition, that is at x equal to b, this vanishes. For fourth case, in this case both the figures meet at the upper end but not at the lower end. So, eta equal to 0 at x equal to b, but non-zero for x equal to a. By Euler Lagrange equation, right hand side of 8.13 vanishes. This finally gives the variation of j, delta j, equal to epsilon into eta into first order partial derivative of capital F with respect to y dash equal to 0 at x equal to a. As eta equal to 0 at x equal to b, so this vanishes automatically at x equal to b. Hence, in 4 cases we found that delta j equal to 0, which gives that Euler Lagrange equation is satisfied, that is y satisfies, small y satisfies Euler Lagrange equation, which is given by this one, that is first order partial derivative of capital F with respect to small y minus ddx of first order partial derivative of capital F with respect to small y dash equal to 0 for a less than x less than b, with the conditions epsilon eta del y dash operated on capital F equal to 0 at x equal to a and epsilon eta into del y dash operated on capital F equal to 0 at x equal to b. If capital Y is not prescribed at an end point, for example at x equal to b, such a condition is called natural boundary condition. Please note that there are another kind of variable endpoints in which variations can occur both in x and y directions, but here we shall restrict ourselves in the above discussions, that is the case of variable endpoints in which variations occur in y direction only. So far we have discussed isoperimetric problems. Iso means same, parametrics comes from the word parameter. In such type of problem, we have to find a curve of given length which encloses the surface area which are minimum. We have discussed detail about it, and also in this module the variable n conditions have been discussed with different cases.